All right, we've explored closure on adding and consequently subtracting, and multiplying and consequently dividing, because dividing is just a form of multiplication with fractions, and subtraction is just a form of addition, just addition of a negative number. So the question now becomes, what happens when one of the numbers is irrational? So let's say we have a rational number represented by a over b, where a and b are integers, and then some irrational number. Let's say c. I'll use a capital C. Okay? Where c is irrational. Can the result be a rational number? Can it be d over e? So this is a rational number, and we're adding an irrational number, and we want to know if it can be a rational number. Okay? This is an example of proof by contradiction. What a proof by contradiction is, it starts by assume it's true. And then prove that it leads to a contradiction. So assume that a rational number plus an irrational number is a rational number, and then demonstrate it leads to a contradiction. Okay? So let's follow our algebraic steps here. If I subtract d over e from both sides, using our algebraic steps, we end up with a over b. Actually, let's do it this way. This will be easier. Let's subtract a over b from both sides. Subtract a over b. I was going to do 2 steps, but we only need 1. We end up with c, which is an irrational number, we assumed, is d over e minus a over b. But d over e is rational, and a over b is rational. And the closure rule for addition and subtraction says this whole thing must be rational. But we started with the assumption that this is irrational. You can't have both. That is our contradiction. So we have proven the rule: a rational plus or minus rational plus or minus an irrational number must be an irrational number. Hopefully that makes sense. I know it seems a little weird, right? All right, let's look at multiplication by the same rule. Let's say I've got some rational number, a over b, times some irrational number, so this is rational, and c is irrational. And I want to demonstrate that if we say the answer is rational, d over e, that arrives at a contradiction. So proof by contradiction: assume it's true and show it leads to a contradiction. Okay? You may recall that the way to get rid of multiplication is division. And to divide fractions are to multiply by the reciprocal. So c equals d over e times, take the reciprocal of this, b over a. So c equals db over ea. Okay? But we've got the rule of closure again. A rational number times a rational number is another rational number. A rational times a rational is a rational number under the rule of closure for multiplication. That contradicts our assumption that C was irrational. So our contradiction, our initial assumption must have been false, and this can't be irrational. Okay? So it's either rational or irrational. So we have proven that a rational times an irrational must also be an irrational number. Okay? A rational times an irrational must be an irrational number. So if you add or subtract or multiply or divide by an irrational number, the answer is an irrational number. Let me give you some examples of questions you might be asked. Square root 2 times 4/5. That's an irrational number, 1.414, blah, 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 times 4/5. That's an irrational answer. Let me bring up Desmos here and demonstrate again. Remember, an irrational number is a number that has a decimal expression that goes forever and does not get repeated over and over. Okay, so let me do this here. To type square root, SQRT, 2, right arrow to get out from under the square root, times 4/5. 1.1313708499. You can see it's a decimal. It's a long decimal. You can't tell if it stops or not, but this is the most decimals the Desmos will show. So it is irrational. It's a never-ending decimal. Okay? And likewise, that's multiplication. If we do 4/5 plus square root 2, that is going to be a rational plus an irrational. The answer is irrational. Let's verify that with our calculator. 4/5 plus SQRT 2. Again, you get a decimal that does not repeat and does not end. Goes forever. Okay. Now, I do want to address one question that may have occurred to you. What about an irrational number plus another irrational number? The lesson doesn't address that. And it doesn't do it because there actually are cases where you can add two irrational numbers and the answer would be rational. Let me give you a case in point. Okay. Let's take this number, 1.1001000100001, etc. You can see what I'm doing. I'm adding another 0 in, so it can't be written with a repeat bar. But that is an irrational number. Okay? And let's write another irrational number, 0.101001000100001000001, blah, blah, blah. That is also an irrational number. Okay? If I subtract the bottom number from the top number, I get 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on. Or 1, which is a rational number because it can be written over 1. Okay? So just be aware that when we do rational or irrational, plus another irrational number, the answer could be irrational, but it is possible for it to be irrational as well. So it's going to be irrational or rational. Most of the time it'll be irrational. This is kind of a rare case. But I thought I should answer that question. You won't be asked it on the test. So for the test, a rational plus an irrational is irrational. And a rational times an irrational is irrational.